Good morning.
Hey, good morning.
Good morning.
Coming to you live from the hills of Jacksonville. Let's see, let's organize our junk here a little bit and wade into the concept of a sequence and the series. Feeling the need for shade.
I watched yesterday's lecture. I was thoroughly upset. I thought we left integrals behind us. And then
I love you, Eve. You're awesome. And then there they were.
yeah, they're raining on our parade. And this is Calc 3.
Come on, man, give us something different. Well, they'll pop up here and there. Derivatives and integrals will pop up here and there. They're your friends now, right? You want your friends to pop over from time to time, don't you?
Eh.
You're thoroughly upset. Thomas is thumbs up on that, so I don't know. Yes, let's see. Anybody not here yesterday? Johannes, did I see you yesterday? Haven't seen you in a year or so. Good to see you again, my man. Let's see.
Good to see you too.
You were working at a restaurant in Ashland and trying to keep up with calculus. Is that
Yeah, in the last year, I was laid off from the restaurant twice, so I've been working out in Grants Pass.
Yeah, imagine that's the case. Brutal. This is
Yeah.
not an easy time to be in the restaurant game, is it?
Yeah, not easy this last year.
No, well, I'm glad you're still alive in the world.
Yeah, you too. Thank you.
Let's see, Ben, you took calculus last year and then thought, let's take the rest of it. And you didn't take Calc 4. Am I remembering that correct?
I did take Calc 4.
That's what I thought. That's
So I just kind of skipped Calc 3. I don't know why I did that, but I had some other classes to take. Yeah.
And are you bringing this on board because of a prerequisite for studies later, or because you have the time and are interested in
Yeah, I guess I do need it for for engineering degree I'm going for. So
Got it. Okay. Sweet. I'm sharing a screen. Got a delicious cup of coffee sitting next to me. Let's see here. I think the iPad is awake now.
I had a question. Are the problems on MyOpenMath the same as in the book?
No, that's one of the things that's one of the reasons I hid a lot of the questions so that I can really go over them, because the book is Pearson and they have their own homework system that goes with it, but that costs a bunch of money. And so we're experimenting with using MyOpenMath, but the classes that people have invented in MyOpenMath don't necessarily match this book. And so the knowledge is definitely in there, but the questions don't line up necessarily. And I am trying to pick those through very carefully. But I invite I don't know if the right word is criticism, but I invite your questions in that regard. I'm going to, in a sense, do a little bit more teaching to the assignment than I would typically do. But yeah, the questions are not coming directly out of the book, and so that's not ideal. And so the ultimate question is that, does it matter that much? Is it, in the end, is it like, yay, we didn't have to spend as much money on this class? Or, it would be equally not surprising to me if somebody said, no, I would have rather spent an extra whatever $150 and had them line up. So we'll discuss that. I mean, I'd invite your criticism about that. Because I'm trying to make this class, match, if you will. Keep it cheap for you guys is really the motivation.
Okay. And are we going to be doing any problems out of the book? Or are we just learning the material that's in it?
Yeah, material that's in it. The book is really going to be a supplement. I will assign, other random things in this class, but I'm never going to say, page 19, questions 6, 7, and 8. It's always going to be coming straight out of MyOpenMath. Really, My open math is the practice that ideally you're just getting immediate feedback in the middle of the night. You get 3 tries in every question, and there's sometimes videos linked to them. And so your ability to get those questions done, I think there's a lot of help associated with it. What I'm most concerned about is the is the tests, in the sense that I'll have reviews in my open math for you to look at and so forth. And I'm hoping to make that really clear. I give really extensive reviews before tests, both to give you practice and also to tell you what I think is important, because I don't think that should be a secret. And we also have a review day before every test, just so we have a little time to break that down on the syllabus. So that's the majority of your grade. So, so yeah, please ask tons of questions and weigh in on things. Where'd all your hair go, Johannes? I remember you having long hair.
Oh, I gotten a haircut recently.
That wasn't, what do you go by though? I've forgotten what we call you, because it wasn't Joe.
I go by Joe just for ease.
Yeah, that's what I thought. That way you don't get called Johannes instead of Johannes.
Yeah, makes it a lot easier.
Outstanding. Well, looks like some of us are here. Cool. So this whole thing, this whole study, at least the beginning of this class, hangs on something called a sequence. And to start with, you might think of it maybe in a practical sense. And really this whole chapter is just kind of an intro to sequences, to sequence, and also its cousin, a series. So you should know what those are. But as an example of something practical anyway, a sequence might be, hey man, I planted a tomato plant and it was, 7 inches tall when I planted it. And then I went back every week and I, remeasured it because I was just curious how it was doing, and it went to 9 inches the next week. And then it went to 12 inches. Notice even from that alone, that pattern is confusing. Like it grew 2 inches. What would have been really wonderful is if that had been 11, because you'd say, hey, I see a pattern. It's growing 2 inches a week. Next week, it's 13 inches. And so it's very easy to recognize the pattern of that sequence. But as you know, maybe from regression and previous, there's equations that model things that are exponential. This one would be linear. And so that's kind of the idea behind a sequence. It's just really a list of numbers. But of course, we're going to do something a lot more, be quiet, phone. We're going to do something a lot more theoretical with this than try to grow tomato plants effectively. And really the idea behind a sequence is just to say, well, notice it's not an ordered pair, but you could make it one, as I just said, by saying, well, this is week 1 and this is, or actually it'd be week 0 because you planted it, right? You planted it then, and then after 1 week, and then after 2 weeks, and after 3 weeks. And so now we have a ordered pairs, if you will. But then, what if the pattern like blows up at this point, and then it goes to 15, and then to 20 or something like that. Well, now it's like, oh man, I don't really understand, what's happening with that now. Is there an equation that models it? So forth. So the sequence is where it's just a list of numbers. Super simple sequence. There's one right there, list of numbers, just a list. It's super simple. So let's take a look at a theoretical example, and I'll show you, as I mentioned before, there's some breathtakingly cool results from this, but we got to build a foundation for understanding some of those things before we can talk about them. So you deeply, really, if you walk out today knowing the difference between a sequence and a series, you got it. Well, let's play around with it a little bit. Well, actually, I'll write it here just since I wrote the word series here. A series would be if you took those numbers and then added them. Would you agree that in the case of a tomato plant, that makes no sense whatsoever? Why would you add them? Like that makes no sense at all. But a sequence is just a list, series, add them together. And in this class, we're going to be adding them together. That's going to be our main goal, is adding them together. And again, I'll kind of show you why in a little bit. Easy questions. If I gave you a formula for this, so this is kind of an example of the kind of thing you might see in a book. If I gave you a formula, notice before I just kind of listed them out randomly off the top of my head, but if I gave you a formula, if the numbers kind of popped out as a result of a formula, and this formula we'll say is an equals 3n minus 2 over n squared. Now, this a thing is something that you're going to see in your assignment in the book and so forth. And all that is just a generic way to say, hey, here's how you get the terms, each term. And so this is the 7 is the first term and the 9 is the second, or, you know, that was the 0th term as well. But let's just say this, let's just say we're going to have n be 1 and then 2 and then 3 and so forth. So that's kind of the way a sequence works. It's like the first number, the second number, the third number, just like I did with the plant. So, oh, well, this is ridiculously easy. It's almost embarrassing. Like, what is this even doing in a calculus class? So you mean you just plug in, to get the first term, you just plug in n is 1. 3 times 1 is 3 minus 2 is 1 over 1 squared. So a1 is 1. Is that what you mean? Like put 1 in there? Yep, that's what we mean. Then I stick 2 in. 3 times 2 is 6, minus 2 is 4. 4 over 4 ends up 1 again. Isn't that kind of weird? Did I get that wrong? I got one of these wrong, didn't I? 6. No, I didn't. And 3. Yeah, I did get that wrong. I had it right in my head, but I didn't get it right out loud. 2, 6, or 4, 4, 4. It's 1, right? Isn't it 1 and 1? And then when I put 3 in, 3 times 3 is 9, minus 2 is 7, over 3 squared is 9. Now they start getting a little weird. And then fourth term, 4 times 3 is 12, minus 2 is 10, over 4 squared is 16. I guess I could reduce that to 5/8. But notice the terms are kind of really strange looking. Like had I not given you the formula, you never would have figured out kind of, you know, what's the rhyme or reason? Where are these kind of things coming from? So kind of a strange thing. And so, you know, half of your assignment questions are this dull or this simplistic. Just list the first 5 terms in the sequence, or they'll say, here's the formula, and use your graphing calculator, you know, plug this stuff in. Don't do it in your head and get it wrong for some dumb reason. But they'll just say, skip all the way ahead and, you know, list the 9th and the 10th number. And notice, because you have a formula, that's really easy to do. You don't have to just, you know, find all the ones in between. You can just say, oh, stick 9 in. Great. 27 minus 2 is 25. 9 squared is 81. Boom, there it is. I got the 9th term. I didn't need any pattern. I don't need to find the 5th, 6th, 7th, 8th in order to get there. Just plug the number in. It's not complicated. Now, just for the fun of it, even though it won't be fun, let's go way out to, I don't know, 28. Now I think, I better not get this wrong, because those are going to be some really big numbers. So now I feel like I need to bust out my machine for the first time. So if I say 3 times 28, that's 84, minus 2 is 82. And then 28 squared, boom, big number, 784. Again, this looks fairly easy and irrelevant. Would you agree with that right now? Now, one of the things we'll concern ourselves with in this class, though, is, and again, I'm just trying to give you the overview of all of kind of chapter 10 and one of the cool things that this does. Let me ask you this question from calculus. What is the limit of a of n as n goes to infinity? That statement should mean something to you from calculus. Do you understand what I'm asking there? And can you answer that question? I'd encourage you to make a conjecture out loud.
When we plug infinity in for n, and the top would be infinity over infinity, so would it be 1?
Awesome conjecture. I'm not going to answer that just yet. So Raymond's hypothesis is if you plug in a number like infinity, again, infinity is not technically a number, that maybe you would get 1 because you have infinity on the top. Like taking 2 away from infinity is not taking anything away from it, right? So you have infinity over infinity. So it looks like this is on its way to 1. So that's our first conjecture. Conjecture is an educated guess. Because you've had calculus, you can make an educated guess. If somebody hasn't had calculus, not going to be an educated guess.
The power on the bottom is greater than the power on the top, so it's going to trend towards 0.
Second conjecture, Vale is thinking the bottom out infinity is the top. Like there's sort of like 3 infinity on the top, but on the bottom there's infinity infinities. I mean, isn't that what n squared means? It means n times n. So Vale is saying, I think the bottom is going to outrace the top. And so it'll go, now get your calculator out, like plug in not A28, but 9,999 or, you know, something like that. You can answer this question old school is what I'm saying. Just start plugging in bigger and bigger numbers and you should be able to see. Now I left my answers as fractions, but your calculator is going to punch a decimal out for that. I think this is a great, I mean, I couldn't have paid you two guys to say better questions than that because I think these are the 2 possible answers. But you don't have to wait for me to tell you the answer. Go old school. If you have in a sense, want to cast your vote now for one of those 2 ideas or perhaps propose a third based on punching some numbers in.
I'm gonna probably go with Vale. I got a real small number.
What'd you plug in?
I plugged in like 8 9s.
Oh, okay.
And yeah, so I got 3.0 times 10 to the negative 8.
Yeah, I think it's going to be small too. 1 would have made sense if you could cancel out infinity, but you can't. So I think it's going to be a really small number.
Yeah, it's interesting, isn't it? It's not obvious.
Well, if you split them into 2 fractions, you can see that the 2 over n square goes to 0. And then the 3n over n square also looks like it goes to 0.
Yeah, that's interesting. So do you understand what Caesar said? Like kind of looking at this a little more mathematically, you could split that fraction up. In other words, to 3n over n squared minus 2 over n squared. Last term, we just finished up with partial fractions and the fact that, hey, that's a fraction before it's been added. So we could split it up like that. And then this n cancels with this n. So you end up with 3 over n minus 2 over n squared. Maybe there it is a little easier to see. But again, I want to highlight it really does go to 0, but I don't think that's obvious at all. It's a question, and infinity started to make people go crazy early in mathematics because are there different levels of infinity? So is 3 infinities more than infinity infinities, if you will? Excuse me. But yeah, actually what you see here is indeed the limit of this goes to 0. And so what becomes interesting then to mathematicians then is what if you then, since those terms go to 0, then what if you switched to not a sequence, since the limit of this does indeed turn out to go to 0. then what would S of n be? So A of n is just the individual terms listed out. A of 28 is 82 over 78. But let's play around a little bit with what a series does with this question. And so if I ask the question, what is S of 3? So this is sort of code for series. What that's saying is don't just give me the third term, but actually sum up the first 3 terms. So in our case, we'd say, well, the first term was, I'm going to write this out just to make sure you're kind of seeing it. This is basically saying throw the plus signs in there. Don't just list them, but now we're going to add them together. And so in this case, if I say, all right, A1 was 1, A2 was 1, and A3 was 7/9, and now I add all those together, I get 2 and 7/9. So that's what a series does. And of course, I could just keep going and it'd become not fun very quickly, right? Like if I said, what is S of 28? Ouch. Like without technology, we're not having fun, right? But let's use technology a little bit here. I'm going to unshare this screen for a second. And the easiest thing I can think of to do some of this work for me is not the graphing calculator, but rather is Excel, because Excel is really good at junk like this. But let's just play around with that formula a little bit. So let's see, I've got one, and again, I'm teaching you a little bit of Excel here in case you want to use this as a tool for assignments, because one of the things that's really cool about the world you live in, we discussed this a little bit yesterday, but the people that invented this stuff did not have these tools. And you and I can blue collar this a little bit. Like we can actually just go look at it as we just did a second ago. We didn't have to theorize about what the limit of 3n minus 2 over n squared was. We could just go punch numbers in calculators and kind of, blue collar our way to the answer. So if you grab both 1 and 2 and kind of drag them down like this, the Excel kind of recognizes, oh, I see your pattern. As a matter of fact, it says, I see that as a sequence of numbers. You went from 1 to 2. So I see what you're doing. You're adding 1 each time, and then it adds 1. So notice that was a really fast way for me to list the first 29 numbers. Now, to get our numbers, did we not do this? Did we not say, well, I will take, this cell is going to equal 3 times this number over here minus 2, and then divided by that number squared?
I think you need to put the top in parentheses. Otherwise, it's going to think that you're just dividing 2 by 2.
Nice job. And so notice that worked, but it worked out of luck in this case. And it worked, actually, I don't know why it worked, but you're right. And I kind of did that on purpose. Usually I make mistakes on accident, but this is one of those rare times that I did it on purpose. You do need parentheses there to make that work. Now what's cool is if you drag that down, notice the second cell automatically updates from D4 to D5. If you're in my class last term when we did one of the projects about the normal distribution and so forth, you probably feel pretty good about this. But notice now that I've done this, I can just drag that down. And so there's the 7/9 number, right? So now I can say, awesome, mission accomplished, boom. And so 28, I figured out a minute ago, that was 82 over 784. Well, there's the decimal equivalent of it. And so now I could just actually grab these and kind of, drag them on down a while. Like now we're down, hey, boom, we got 500 numbers here. So you can certainly see the individual terms are going to 0. So the question that this class ultimately tackles is, well, if those individual terms are going to 0, and we just kept on going, and I won't go crazy with this, but this is fairly crazy. Just like I told you yesterday, the question is how quickly are these going to zero? Notice down here, by the time we get to the 1,150th number in the sequence, notice they're not changing that much. Like this one went from 0.002609 to 0.002607. So that only changed by, what is that, 2 10,000ths or whatever, tenths, hundreds, thousands, 10,000s, hundreds, millionths. It only got smaller by 2 millionths than the previous number. And so it turns out that if this is going to zero quickly enough, then this sequence or this series might actually add up to something, even if we had infinitely many terms. And so we're going to only be touching infinity in this class. We're only going to add stuff up when there's infinitely many terms. We're never going to add up the first 7 of them. You don't need to know calculus to add up the first 7 terms. You just grind it out. But we're going to add up the first infinitely many terms. Oh, that's all of them. We never get to quit. Does it actually add up to something? Does that approach a limit? Well, I would ask you that question here. Do you think this will approach a number? Do you think this will approach something? Of course, I can I can grab all of these terms here, which I guess is taking forever. Notice they're getting bigger and bigger and bigger as I move up. And so do you agree that this sequence, do you agree that this sequence is decreasing? That'll be something we'll talk about a little more formally in the next section. But do you agree that it's decreasing?
Yeah.
Definitely decreasing. Well, except for the first 2. Notice that's kind of weird. It goes from 1 to 1. Like it isn't always decreasing. Like it kind of didn't decrease there, but from then on it decreases constantly. And so, you know, again, these are the kind of things the mathematicians nerd out over. Like, can we say this is decreasing, or do we have to make an exception for the fact that the first term didn't? And so do we make up a whole set of terminology for this and say like, well, it's sometimes decreasing, or it's ultimately decreasing, you know, or can we just say it's decreasing and get on with it? But notice down here on the right, can you see this, by the way, where my cursor is, or is that really tiny? There's a little kind of a cheat down there that tells me, hey, you've got 1,164 terms down there, so I don't have to write a formula to tell me how many I just grabbed. But the other thing I often want to know is the sum, and notice it says the sum is 19.62. So if we added up infinitely many of those terms, do you think the answer is infinity, or do you think it tops out at 20? Or do you think it tops out at 22 or 28? Or maybe
tops
it's
out.
maybe it's some crazy number like, you know, pi cubed over 3 or something weird like that. Can you at least see why mathematicians would be interested in this idea? And again, the fact that it comes out of the weird, you know, strange mind of a mathematician and becomes something practical and worth learning, so that you're forced to take this class for the fact that there is actually a neat reason to know how to do this is pretty breathtaking.
What is the application for this?
Yeah,
in the real world.
It turns out that you can rewrite, probably the simplest example of that is, I mean, just stop and think for a second. How does your calculator know what the logarithm of a number is? I mean, we take that for granted. But if I say, I'd like to know the log of 81.6, and so I take the natural log of 81.6 on my calculator, it spits an answer out. Remember, what that's doing is answering the question, e to what power is 81.6? And so it's like, how does the calculator do that? Well, it turns out there's an infinite series that you can replace natural logarithm with, and then program into a calculator in kind of an iterative fashion. And that's why you have a calculator button for it. Like, you would not know the natural log of 81.6. We take that for granted in the last 40 years, but nobody in the history of math knew what the natural log of 81.6 was. Or they would sit there making a rough calculation for days on papyrus. They didn't even have add, subtract, multiply, and divide calculators. And so the fact that we have a calculator that will do all of them, it turns out, not just natural log, but also sine, cosine, tangent, all of those other ones. Those aren't just stored in your calculator as a list. If you think about it, probably there's no human in the history that's ever wanted to know the natural log of 81.6 5 2 3 4 8 9 6 4 2 1 7 9. Like there's probably no human that's ever done that. And yet your calculator will tell you the answer to that question. It's because it's, you know, what is it doing inside there? I mean, that's kind of one of the beautiful applications of this.
I thought it was interesting in the book they mentioned infinite series are used to determine in medicine how much of an antibiotic someone will have in their system after a week.
Yep.
If they're given, you know, a routine dose.
That's exactly right. And we'll be tackling that in a couple of days. But in the end, if like, let's say you take a drug of some kind, either legal or illegal, and 10% of it is left in your body tomorrow, does it make sense 10% of 10% would be left in your body the next day? And then 10% of 10% of 10% would be left in your body the next day. And so it kind of just starts decreasing to nothing. And so the people that are taking a medication every day, so they take it one day and then there's 10% left, but then they take it again and now there's a brand new dose plus the 10% they already had. And so, you know, what's going to happen over time? And so, yeah, there's some genuine applications. This is also an application of like how compound interest works when you have a house payment or something. So yeah, there's some more tangible applications. So what's your conjecture? I just added up the first 1,164 terms and I made it to 19.62. Do you think this is going to converge to a sum that is like it actually stops and goes no higher, maybe 21, 28, 30? Or do you think, no, if you go far enough, you'll make it to 20, you'll make it to 40, you'll make it to 80, you'll make it to 10,000, you'll make it to 500,000?
You know, the mathematician in me wants to say it's going to keep going because we can't actually touch infinity. So if you keep going, you're going to keep adding more numbers and eventually it will build up. But I feel like this is a trick question. So I'm not sure.
He was like, I know you. Yeah, I mean, it really is. It's a tricky question. It's not a trick question, but it's a tricky question. My gut reaction is it feels, I mean, we have 1,000 numbers here and we saw them going to zero. So the fact that the sequence, very important, the sequence went to zero means this does have a shot at adding up to something, even though there's infinitely many terms. And that's what we saw yesterday. What's the area under that curve? Sometimes it got close to the x-axis so slowly that the answer to the area under the curve was infinity. Other times it got to the curve so quickly that the answer actually added up to something. Turns out this one's infinity. Although it looks like it's going really slow, everything in me wants to think it's never going to make it to add up to 50,000. And you can see why this is ultimately needs to be proven, if you will, because the first 1,100 terms only got us to 19.6. And so, man, how many terms do you have to get to 50,000? Like, it just doesn't seem possible, does it? But that's kind of, you know, part of what this class really, really deals with. So, yeah. I just want to, I don't know, I guess acquaint you with a bit of the mystery of this, the curiosity of it, both practically and impractically. Well, let's back off of that for a second and just, I don't know, play around with the things you really need to know for this section. And then we'll go back and look at maybe some of the mystery of it a little bit more. So do you see, the main thing I want you to know right now is, do you see the difference between a sequence and a series? Like, those words need to mean something to you. Otherwise you're going to look at an assignment and kind of be like, what are you asking me to do? And make sure you see that as like really simple. Sequence, list of numbers, series, add those numbers up. That's it. Add the first 28 numbers. And after today, or maybe tomorrow, we're not going to ever add up. It's always going to be infinity. We're never going to add up 28 numbers. That's just add them up, write them down and add them up. Like, there's no point in that. We're interested in infinity. Ultimately, this class, Math 253, at least chapter 10, find S of n, or I'll say as n goes to infinity. And that will be pointless unless each term goes to 0 as n gets really large. In other words, if you're going to add infinitely many terms up and they're going to add up to something, then each the term way out there has got to go to 0, right? If I take the sequence of my plant up here and I say, what's the limit of that series? I'm going to add them. What's the sum of that series as n goes to infinity? Well, the terms are just getting bigger and bigger and bigger. Clearly, the series will add up to infinity because it went from 15 to 20. It's increasing, like the terms are getting bigger and bigger and bigger. So if you just keep adding them, there's no way it's going to add up to infinity. The terms have to work their way to 0 before you can have any shot at adding them all up and actually getting an answer. You agree with that? Okay. So there's a couple of classics that you need to understand, and let's look at those now. One of them is called an arithmetic. An arithmetic sequence. Arithmetic sequence. An example of that would be like 7 and then 10 and then 13 and then 16 and then 19. Notice that's very easy to see the pattern. What is it I'm doing every time to get the next term?
Adding by 3.
You're just adding 3 each time. So the fact that you're adding something every single time, or of course it would work for subtraction too. I could be subtracting something every time. But that's what makes something an arithmetic sequence. And to make this look complicated, you have to recognize the fact that you're adding 3 each time. So the recursive definition of this would be this: to get the next term, what do? You take the previous term. Does that language make sense to you? If I say an and an minus 1, that little n represents which term are you on? Are you on the 9th term? A9 would be 9. So I'm going to erase this, but if I said I'd like the 9th term, then what do? You take the previous term and add 3 to it, don't you? I mean, that's what you're doing. That's all that's saying.
So then would the series of this be a sigma sign with your sequence definition of like an plus 3?
Yes, except for we got to do a little better than a recursive definition to make that happen. That's exactly right. So let's answer that question right now. So the recursive definition is easy. That's where you just say, hey, I see what's happening. You're just adding 3 each time. But to actually get the formula, I hated these kind of questions when I was, to actually get the formula, and you may have, when I say I hated these questions, I hated it earlier in math because teachers were always saying, do you see the pattern? And then they would ask you for the formula for it. In other words, would you agree that recursive definition is not very helpful if I said, I would like you to tell me what A224 is? You can get it, but you're going to sit there and have to go plus 3, plus 3, plus 3, plus 3, like a lot of times. And then finally you could answer the question. The recursive definition doesn't really help you. You can't jump straight to the 224th term in this sequence. Do you understand that? A second ago, I gave you the formula. I gave you the formula. And so it was super easy for us just to jump straight to the 28th term, right? Well, that's the question here. How do you get the formula? How do I figure the formula out? And I want to be able to do this I want to be able to reason it out for myself. some of you might kind of have an answer to this, either based on something you've studied before. I don't want to give you a memorized definition for this. You can look that up in your book in 10.1, but I'd rather you just reason it out. Like to get to 19, well, we started at 7, did we not? We started at 7, and then we went +3, +3, +3, +3. So we took 7 and we added 4 3s to it, and that got us 19. Do you agree with that?
The 4 would be your x. So it'd be 7 plus 3x. Because that changes depending on which number you're going on.
Yeah. So let's go like a couple more out. Then a couple more out would be 7 plus, well, it's still a bunch of 3s, but it's 1, 2, 3, 4, 5, 6 3s. And that would get us out to 25, right? Notice that 19 there is, well, this is 7 is the first term, 10 is the second term, third, fourth, fifth. So 19 is a 5, correct? That's the fifth term. And 25 is actually a 7. And let's do one more.
So Doug, would your formula, if you wanted to find just any number in the sequence, be that number minus 7 divided by 3?
Yeah, that's exactly where we're going with this. I'm not going to answer that just yet because I want to give everybody a chance to kind of soak on this. Like figure the formula out for yourself. So for instance, if I added 3 more 3s, 1, 2, 3, 3 more 3s, that'd be 9 more. So that'd be 34. Then that's 1, 2, 3, 4, 5, 6, 7, 8, 9 3s. So 25 is a 7, 34 is a 7, 8, 9, 10. That's the 10th number in the sequence. So this is a 10. Do you see that oddly, when you're adding, what you're doing is repeatedly adding 3s. Repeated addition of 3. Well, that's why humans invented multiplication. Do you notice that I used multiplication in my formula for that reason? Like if you want to add a bunch of 3s, then just multiply by a bunch of 3s. 34 is 9 3s that you added to get out to the 10th number. You have your starting number. So do you agree that this is kind of your start? And this is kind of your change. Let's see, what do I call that? Your change. I guess I'll just leave it at change. Since it's arithmetic, the change was 3. We see that we're repeatedly adding 3. So that's our change up there. And then the 9. So what about the 9, 6, and the 4? What about these? Like, can anybody tell me now what a to the 35th would be? We know it's 7 plus some number of 3s. Do you agree with that? That part's the same in every formula. But the question is, what's the multiplier? What do you notice?
It's 34 times 3.
Why is it 34? What pattern do you recognize?
The multiplier in each of the examples that we did was 1 less than the term.
Precisely. In other words, this was the 10th term. And because we started with 7, 7 was our first term, then there's always kind of 1 less 3s that we added. So if we're on the 10th term, there'd be 9 3s. If we're on the 7th term, there'd be 6 3s. If we're on the 5th term, there'd be 4 3s. So you're exactly right, Joe. It'd be 34 of them. And so now that I recognize the pattern, I think I can actually answer that question. So now we're in a position then to actually write the formula down. Would you agree that the formula then is 7 plus, and again, what is it? You know, what's the formula I'm actually after here? It's the formula for any term, you know, the AN term. Isn't it 7 plus, well, you tell me, what do I write here?
N minus 1.
One less, just like Joe noticed. Eve's exactly right. You take whatever the term you're on, you want the 10th term, then this is N minus 1. Now that's the formulaic, but notice I didn't just give you a formula that the book gave you. And this is what I remember being given to me and thinking, man, that's hard. I don't understand where that came from. But I've taken a little bit of time to help you understand where it came from. Let me show you an easier way. Here's the way I think about this. If you recognize that you're just repeatedly adding 3, so this is the formula kind of by pattern. But this is an easier way. The formula based on seeing that you're adding 3 each time. If you see that you're adding 3 each time and you say, hey, I'm repeatedly adding 3, that's multiplying by 3. Then just immediately say the answer is 3n, because that's what you're doing. You're multiplying by 3 each time. But then say, well, that doesn't take into account where you started. Do you understand that? In other words, this time we started at 7. So how do you make this equal 7 at n is 1? In other words, isn't a1 equal to 7? So how do you modify that to make it work? If n is 1, 3 times 1 is 3. The only way I'm getting 7 is if I add 4 to it. Fixed. So does it work? If you put 2 in, do you get 10? If you put 3 in, do you get 13? If you put 4 in, do you get 16? Is it working? I like that too. I don't care which way you use, but like a book would give you a formula for this, and I have no problem with that. That's why I showed them to you both. They'd say this is the start number, this is the change, and then you just throw n minus 1 in there every time. If you're a good memorizer, then that will work. But I just don't like it because I don't understand it unless I made it for myself.
And we would have parentheses around the n minus 1, right?
Yeah, I'm not being super careful about that. That's exactly right. Maybe we should throw those in there just to be a little more clear. So I don't care kind of what method you use, just be able to get it. I guess that's kind of the idea here. Okay, your turn. I'll give you a little. That's not quite as obvious that that's an arithmetic sequence, but see if you can find the formula. First of all, recognize, hey, yeah, that is an arithmetic sequence. I'm adding the same thing every time to get to those terms. So you've got to recognize your change. You've got to recognize that, hey, every single time I'm subtracting 7, this doesn't be a positive number. You're adding -7. Hey, I'm going -7 each time. -7, -7. What am I doing? I'm repeatedly subtracting 7. Well, repeated addition is multiplication. So in my way of thinking, oh, cool. Well, then I already know the answer is -7n. It's -7 times n. But then I need n equals 1 to produce 5, right? Because this is the first number, the second, the third, the fourth. So when I stick n as 1 in here, do I get 5? No, I get -7. Well, how am I going to get 5? If I add 12 to it, I'll get 5.
Should it
And then
be at n equals 0 is 5? Or
Yeah, now this is something we haven't talked about yet, but this is assuming that you think of the sequence as the first, the second, the third, the fourth number. You can think of the first one as A0. In other words, it's the 0th number in the sequence. So I'm just looking at it as n equals 1, n equals 2, n equals 3. And so in a sense that has to be stated, and we'll talk about that a little bit more. But Cheyenne does point out kind of a bit of a conundrum. Is the first one n is 1? And typically the answer to that is yes. But as I said, like in the case of the tomato plant, when you first plant it, you could think of that as 0. In other words, that's when it was born. That's what you do with kids, right? How long are they when they're born? Oh, they're 21 centimeters. And then at year 1, they're 25 centimeters, right? So you start at 0 because that's like birth. And so that's a problem that we got to deal with. So I'm glad you brought that up.
Hey Doug, real quick, can you do an example of that on this one? Because I started out as 1 and got -7n plus 12, but I don't see how it would work on the second one.
So now I put n as 2 in there just to make sure I didn't screw it up. So that's -14 plus 12. Yeah, that's -2. It's working.
No, I got that. But what Cheyenne was saying, if you put 0 on 5, then you'd have
okay.
-7n plus 5 as your formula. And then how would it work on -2, which would have to be 1?
Yeah, so if you said I want n to be equal to 0 and then 1 and then 2, then you're right. The formula would be -7n plus 5. And so that would be, so that works. Notice if you put 0 in, you get 5. If you put, then this would be the first term, right? If you put 1 in, don't you get -2? So that's the 0th term.
Oh, yeah. Okay.
That's the first term. This is the second term. So it works. So yeah, it's kind of interesting. You get a slightly different formula depending on whether you call the first term the 0th term. As far as your assignment goes, and as far as what we're tackling right now, it's never going to be 0, 1, 2. It's always going to be 1, 2, 3, 4, 5. Because when you see a list of numbers, you never say the first one is the 0th term. You say that's the first kid, that's the second kid, that's the third kid. You always kind of start at 1, like the counting numbers. Again, as I said, there's nothing wrong with just saying, no, I like formulas. I'm a good memorizer. I'm just going to use the formula. The formula says take the first number in the sequence 5 and add to that the difference times n minus 1. Boom, done. Same answer. Notice if you multiply that out, distribute that out, these are actually equal to each other. They're the same formula. -7n plus 7. Oh yeah, 7 plus 5 is 12, but they're the same exact formula. So they're both good. I'm not really sure which one. I don't like anything I have to memorize because that means I won't know it. I won't know it a month from now, which means why even learn it? Because I don't know it anymore. I want to be able to reason this out, build it for myself if I ever need it for something. So arithmetic sequence is a big one. Let's take a look at the other. There's only 2, fortunately. Let's take a look at the other big one, which is called a geometric Geometric sequence. Let me quickly tell you why somebody came up with the name geometric for this. Let me ask you this question. Here's a physical, interesting question. So there's a square. It's probably in your book somewhere. This is one of the classics. And so you decide you are going to chop the square into 4 parts, and then you are going to color this in. So you have 1/4 of the square. Does that make sense? And then you do the same in this upper right-hand corner, and then again, you color the lower left-hand square in. So now you have 1/4 plus 1/4 of 1/4, don't you? If I'm deciding I'm adding this up. And then I repeat. And now I have 1/4 plus 1/4 of 1/4 plus 1/4 of 1/4 of 1/4. And I repeat. How long am I going to repeat? Because this is
Isn't this 1/4 plus 1/8 plus 1/16 plus 1/32? Or am I thinking about this wrong?
You're thinking close, but that's not true. So I could probably survive one more of these. So if I ask the question, what's the area of that if it goes forever? Again, it's only an interesting question if it goes forever. But that's a geometric sequence. Well, it's geometry. So these sequences arise because of geometry, because you have 1/4 plus 1/4 of 1/4 plus 1/4 of 1/4 of 1/4 plus 1/4 of 1/4 of 1/4 of 1/4, and so on and so forth. What's a boring example of a geometric sequence? Something like this. 6, then 12, then 24, then 48, then 96, and then I bet you see the pattern. Now, what's the recursive pattern to this? How do you get from one term to the next? How do I get the next term? What do I do to the previous term? I know it's obvious. Somebody say it.
Multiply by 2.
Thank you. You're just multiplying by 2. Notice in the previous one, you were adding the same thing every time, but this time you're multiplying by the same thing every time. Last time it was repeated addition, which we call multiplication. This is repeated multiplication. What do we call repeated multiplication?
Power?
Power. I like the tone of voice you said that in. Like, I'm pretty sure the answer is power, but I'm not totally sure. So we have a way of writing that. So notice, again, that recursive definition is important to recognize because that's what tells you this is a geometric sequence. But that does not help you get the 79th number. Not helpful. If somebody says, I'd like to know the 79th number in that sequence, because I don't have time to multiply by 2 that many times. You understand that? But I'm going to give you a second to think about this. Figure it out yourself. Aren't you going times 2, times 2, times 2, times 2? And we say by convention, this is the first term, this is the second, this is the third, this is the fourth, this is the fifth. Can you use the logic I just showed you a second ago to create the formula for this? The much more complicated question, what's the formula for AN, so that I can answer questions like A79 without having to work my way up, getting all previous numbers to get there.
Well, it's a quarter of the previous size every time, right? So couldn't it just be 1 plus 1/4 plus 1/16 ...
Yes. Now don't confuse this. this was a kind of an introductory example that has nothing to do with 6, 12, 24, 48, 96. I'm only asking about 6, 12, 24, 48.
Gotcha.
Right now.
Well, it would start out with a 6 plus something else, right?
Yeah, like build it, like to get to 96, just kind of play around a little bit. That's what I'm saying. Play around just like we did last time. Like to get to 96, didn't I take 6 and then I multiplied by 2, 1, 2, 3, 4 times. I multiplied by 2, 4 times, and that's how I got my 96. Isn't that right? It's the same logic that we just used a second ago. So this is like the start term or the first term, whatever you want to call it. And that 2 is your change, if you will, or your multiplier. I'm going to call it, maybe I'll call it what your book calls it, your ratio. Because that's how you find this. Like if you take 96 divided by 48, you get 2. If you take 24 divided by 12, you get 2. That's your ratio. So change kind of implies subtraction. That's how you're getting it. And this is not arithmetic. Because I add 6 and then I add 12 and then I add 24. It's like, so I'm going to have 6 and 2 in my formula, but what's the 4 represent? If I want to get way out there, then what's my formula? It's going to be 6 times 2 to what power?
And minus
Mhm.
Yeah, just like last time, it's 1 less. Because you started with 6. 6 was our first term and it's sort of not in it, then you just say 6 times 2 to the n minus 1. So there's your formula. Now you can get out there to A79. By the way, what's your calculator say? 6 times 2 to the 78th power is 6 times 2 raised to the 78th power. Huge number.
So if we're just given a set of numbers and we're not told which sequence it is, you would have to build it from scratch to know which formula to use.
Well, you just have to stare at it and say, what is it I'm doing? Like my first thought when I look at this is to say, oh, look, 6 and 12, I'm adding 6. But then I go here and realize, oh, I'm not adding 6. Like the next number would be 18. So I guess it's not arithmetic. Like I'm kind of slow. Like I would look arithmetic first because it's kind of easy. And then I would say, well, oh, 6 times 2 is 12. 12 times 2 is 24. Oh, there's the pattern. It's times 2 times 2 times 2. I'm multiplying by something each time. And again, these are just easy patterns and they're also practical. Let me give you a quick example of a geometric sequence. Actually, before I do that, let's see if you can find the formula for this one. Notice times 2 is pretty easy. I'm going to give you one that's a little messier. What about 6 and then 2? Notice at this point you can't tell what it is. It could be arithmetic because it's -4, or it could be geometric. What would I be multiplying by here?
One-third,
1/3.
if you're multiplying.
And because this is geometric, I am multiplying by 1/3. So could you write the formula for that now, based on the pattern that we just saw? First term, second term, third term, fourth term, fifth term. I'm repeatedly multiplying by a third. Repeated multiplication is exponents. So you started with 6. Your multiplier is 1/3. You're multiplying repeatedly by 1/3. And you always end up with 1 less than whatever number you're at. So there's a pattern. So let's see, I want to check my work. So clearly the 6th number, the top just stays 2 every time, and the bottom seems to be, let's see, 27 times 3 would be 81. So a to the 6th, check. A to the 6th. Do I really get 2 over 81? Question mark. Let's see, that'd be 1/3 to the 5th power times 6. So I bust out my machine, 1/3 raised to the 5th power times 6. I got 0.02469 and some change. And so because I'm lazy, I'm typing that in, and then I go to math and I say convert that to a fraction. Boom, 2 over 81. All right. So cool. Now in a sense I can kind of box this and say I got it. It worked. Cool. Notice interestingly, when you put 1 in, you end up with 1/3 to the 0 power, don't you? 1/3 to the 0 is 1, and so you end up with 6 times 1. So kind of cool. Now, just a quick example, because this feels very theoretical, and I found myself, the times I saw this in my math career, different places, I didn't connect with it very well because I just kind of thought, why does anybody do this? Like, where would there be an arithmetic sequence? Where would there be a geometric sequence? Why am I studying this? It's fine, you know, some mathematician's bored and sits home at Christmas and invents all this stuff. Great, but as an example of a geometric sequence anyway, if you, practical example. And in a practical sense in your life, this actually might be the most important math that exists. The most money you'll ever spend in your life is most likely on a house, and that will be a big deal to figure out how to pull that off and afford the down payment and begin making payments. And you make those for 30 years. Take your age right now and add 30 to it. As your automatic response is, wow, I'm old. I'm like 1 foot in the grave. Correct. Bought my first house at 25 years old. I am now 54. That means I'm now old, and I've been doing this for 30 years. And it's like, now I'm going to have my house paid off. You're going to turn into me while you're paying this payment. Like, that's a big deal. How does money work? If you put $712 in the bank at, and by the way, this is easy because this is a saving example, not even a payment example. $712, and it was in there at, I'll make this easy on us, 6% APR. Who knows what APR stands for?
Is it annual percentage rate?
You're right.
Or-
It's annual. It's a yearly percentage. It's not a monthly percentage. But when you save money or when you pay a monthly payment, it's a monthly payment and you get a monthly statement. So your money actually grows monthly. So your monthly percent would be 0.06 divided by 12. And that's why I picked 0.06. Most of the time when you divide by 12, you get a decimal that goes on forever. But when you divide 0.06 by 12, you get 0.005. And so that's the interest rate that you are concerned with as a customer if you're saving money. And so if you will, at time, and I'm going to make this a little more complicated by doing what kind of Cheyenne pointed out earlier, which is at time 0, the amount of money you have is $712. I'll put the dollar sign up here. The amount of money you have is $712. But after 1 month, does it make sense you'd have 700? I'm going to speed this process up a little bit. You'd have 712, but you'd take 0.005 times that number, 0.005 times 712. Very disappointing, $3.56. However, that's coffee. You have $3.56 that you get to add to that. Now, a faster way to do this is just to take 712 and multiply it by 1.005. Do you understand that? Because that's 100% plus 5%. If you only take it times 0.005, then you just get the amount of interest you made, $3.56. But if you take it times 1.005, you get all of it added together, right? So 712 times 1.005 is $715.56. So would you agree then after month 2, it'd be taking $715.56 and then multiplying by 1.005 again? But think about that a little more carefully. Isn't that actually 712 times 1.005 to the second power? So you have to round this off, but you get $719.14. Does it make sense, armed with the understanding of this geometric sequence right here, I could proceed out to 2 years, which would be 712. Notice because I started at 0, not 1, notice there is an exact match between n, oops, that's not what I wanted. There's an exact match between n and that exponent right there. So I don't have to say 712 times 1.005 to the 23 like we did a second ago, because I started at 0 this time. So that actually would be 24. You see how I found a pattern? Isn't that exactly what we just did? Starting amount times the R, the ratio, the multiplier, times however many periods of time that's passed. So now I can answer the question, how much money will I have after 2 years of saving this money? Bam, $802.54. That's a geometric sequence. And so you're repeatedly multiplying by the same thing. That's how money works, whether it's working for you in this case, or whether it's working against you in the case of a payment. So money is modeled entirely by repeatedly multiplying by a percentage. And isn't that also true for, say, drugs in the bloodstream? As I mentioned earlier, if you have 10% left of the drug after, say, 1 day, then you're repeatedly multiplying by 10%, so to speak. Or maybe it would be 1 plus 10%, or maybe it'd be 1 minus 10%. But anything that grows by percentages, which is lots of things, is actually modeled by a geometric sequence. Would you agree in this case it makes no sense to add those together? Like I don't get to add month 1 plus month 2 plus month 3 all the way to 24 and then say, hey, great, I have $10 million. That you don't, there's no sense in adding these in this case. But nobody calls it this. And I learned this math, this money math, and I learned geometric sequences, but I never knew they were the same thing. This is why mathematicians thought that was worth a name. Geometric just means you're repeatedly multiplying by something. In boring problems, it's going to be 2, like it was here. You multiply by 2. That would never happen in the real world. Real problems, it's multiplying by either something slightly bigger than 1 because it's growing at 0.5%, Or what if you're losing money? What if you were losing 6% annually? Well, that would be 1 minus 0.005. That'd be 0.995. That would be our multiplier, in which case we're going down, 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 down. That's kind of a bummer. So geometric sequences are actually pretty cool. Okay, let's just look at a couple of, let's just look at again, where are we going with this with calculus? If I asked you this first arithmetic sequence back here, if I said, what's the limit of that sequence as n goes to infinity? 1, 2, 3, 4, 5, 6, 7, 10. What's happening to that if we keep on going? If n is not 10, but now 20, now 50, now 800,000, now infinity. What's the limit of these terms? What are they becoming? What are they doing?
Just going to infinity.
Yeah. So notice that's, I don't know, I guess I want to say not interesting. If you just keep going, the terms get bigger and bigger and bigger. Do you agree this one's the same? They're just getting bigger and bigger and bigger, multiplying by 2 times 2 times 2. The limit of that sequence is infinity because the terms are just getting bigger and bigger and bigger. However, what's the limit of this sequence? This one we did as an example. What are those terms doing?
Getting smaller.
They're getting smaller, smaller, smaller. So that's the one question we reconsider, I guess that's 2. So let's just add this right here since I seem to have some room for it. What's the limit of an as n goes to infinity? It is not infinity. What is it?
Zero.
They're going to 0. You agree with that? When you get way out there, if you take 6 and you multiply it by a third, by a third, by a third, by a third, notice your numbers are getting smaller. With this practical example, do you agree the limit of this one is still infinity? Because you're multiplying by something more than 1. Now it's growing a lot slower than multiplying by 2 times 2 times 2 times 2. It's growing a lot slower, but it's growing. This is on its way to infinity. If you wait long enough, if you live 900 years, you'll be making a lot of money. This is exponential growth, it's called. Early on, for these first 24 months, you don't really make that much money, but go in there and type something like 1,000 in instead of 24. Like you start making bucks. The first month you only made $3.56. But if you go from month 1,000 to month 1,001, you start making a lot of money because you have a lot of money. Month 1,000, you're up to $104,000 now. That's month 1,000. Month 1,001, you made $520 that month. Going from month 1,000 to month 1,001. And 1,000 is not death, right? Like you're just still alive. But you're making $500 a month when you get out to month 1,000. You're making $3 a month when you're at month 1 and 0. That's what exponential growth looks like. It grows really slowly in the beginning, but it really starts to take off later on.
It's like that old adage with the guy who invented chess who wants a grain of rice on each chessboard.
That's exactly right. That's exactly right. Thank you, Cheyenne, for posting the link on Discord. I'm just alerting everybody to the chat because I just happened to notice that. So talking to other people in the class is really helpful outside of class. So take advantage of that. Good observation. Now, because because that limit approaches 0, would you agree the question then, and this is what this class, if you will reduce to, if I considered the sum of 6 times 1/3 to the n minus 1, where n started at 0 and went to infinity. Sorry, Eve, we're back to the genesis or the start of integrals here, which is another way of saying, let's add all of these up. This might not be infinite. Do you agree with that? Since the terms actually work their way to 0, then if we add them all up, this actually might add up to something. Even though there's infinitely many of them, it might actually add up to something. Are you feeling what I'm saying here? This is really important. Are you kind of like, yeah, actually I can see that. And notice these got small really quickly. Do you agree with that? When you look back here, it started at 6, that's pretty big. 2, 2/3, 2/9, 2 27ths, 2/81. That seems to be getting small pretty quickly. That actually might add up to something.
It'll be at least 6, right?
Yeah, well, even better, at least 8, right? Because 6 plus 2 is 8. And then 2/3 is almost another 1. And then 2/9 is like, it looks like it's at least 9, doesn't it? Turns out this one does. Geometric sequences will add up to something. I was about to show you, but I guess we're out of time, so I'll show you later. I will be showing you this at some point, but that actually does add up to something. There's an answer to this. I can't help myself. I gotta show you. Leave if you want to leave. It's 9:21. So it might not be infinity. And it turns out it is not. So watch what's really cool about a geometric sequence. This is only true for a geometric sequence. It's just too cool not to show you. So we said Sn is equal to 6 plus, not a list, not commas. It's a series, right? And we're adding them. Now we're going to add them. And notice we have no reason to. This is just some dumb random bunch of numbers. It doesn't always make sense to add them, as I said, for the practical problem. It makes no sense to add those. 6 plus 2 plus 2/3 plus 2/9. And by this time we say to someone, you can see the pattern, right? So then we say plus dot, dot, dot. And of course that dot, dot, dot implies when do you stop? Never, you never stop, right? What would happen if I went back, since everything is times a third, what if I went back to the same sequence here and I multiplied it by a third? What would I get? Distributive law, I multiply every single one of them by a third. What happens? Well, the 6 times a third becomes a 2. The 2 times a third becomes 2/3. The 2/3 right here times a third becomes 2/9. What do you notice?
You're shifting the starting point over 1.
I wish I could say it any better. Joe said, you're really just, it's the same list. You're just sort of shifting it over. So what would happen then, since these are both equations, and I said something about this a little bit yesterday, but what would happen if I subtracted both of these? What is Sn minus 1/3 Sn? Remember, this is really 1 Sn. What is 1 Sn minus 1/3 Sn?
2/3 Sn equals 6 then.
2/3 Sn. And then 2 minus 2 is gone. 2/3 minus 2/3 is gone. 2/9 minus 2/9 is gone. Everything is gone. And so you just end up 6. You agree with that? Oh my gosh, I just solved for Sn. All I gotta do is multiply both sides by 3 halves and I get Sn is actually 18 halves or 9. So it turns out that indeed is not infinity, it is 9. And again, this needs you should have a chill on you right now, or you don't understand what just happened. How many terms did we just add up?
Infinitely many.
Infinitely many. You can't stop. Like you can't go to Excel and get this answer. Now you can go to Excel and see it on its way to 9, and you could guess it was on its way to 9, but it actually is 9. If you never stop, it's approaching the answer 9. You'll never get it if you go try to do it. But the answer to this, the limit of it is 9. That's crazy. And so this right here, my friends, is what ends up being a powerful truth. We actually are adding infinitely many, we got an answer. Now you did see that happen yesterday too. We said, what was the area under Gabriel's horn? And when it was under one, when it was 1 over x, we said it didn't add up to something, but it was 1 over x squared. It did add up to something. It actually had an answer, even though it was infinitely many, infinitely long. Well, this is no different. It's infinitely long. This is no different than what we did yesterday. It's just that yesterday the formula was 1 over x squared, and today the formula is 6 times 1/3 to the x minus 1.
But the surface area was infinite, right?
Yes. So weirdly, yesterday the surface area was infinite, but the volume was finite. The volume actually approached something. It was mind blowing. Now, again, all this looks like right now is just kind of parlor tricks, like, you know, mathematicians sitting around bored trying to come up with something to play with. And if you're a true mathematician, this is beautiful and worth playing around with. And if it accomplishes nothing, true mathematicians say, I don't care, it's beautiful. When it comes out of that, you know, world of nerds and actually helps people in the real world, then it's kind of a win-win. Like mathematicians are happy, and then the practical people who want to build houses and, you know, build bridges and have them not fall down and so forth, then they're happy too. And so then they say, thanks, mathematicians, even though you're usually weird. I appreciate what you did here because it produced something that, you know, allows us to do something in the real world. That's how you tell, am I a mathematician or am I, you know, kind of a practical person? I myself, practical person. I can appreciate the beauty, but I'm not going to stay inside on a day like this to invent things like this. I'd rather play, you know, in my kayak, for instance. So that's where this is going. I got one other cool thing, but I'm not going to show it to you. So we're interested in the limit of a series. This is the limit of a series. That's what this class is about, the limit of a series. Series implies addition. We're going to add them up. And when that exists, when it exists as it did here, oh my gosh, that's amazing. It only exists because the individual terms went to 0. You have no choice. You have no shot at adding up infinitely many terms if they're not on their way to 0, right? There's no way. But if they do go to 0, then there's a shot. It actually might add up to something. And then of course the question is like, how do you figure out what it adds up to? If it's geometric, there's a pretty cool, easy little technique because you're multiplying each term. That's by the way, the sad part of this is that's the only one. Like there's not easy ways to add up other ones.
Have we covered enough to finish the homework for this section?
Yep, you have.
Okay.
You will be successful with what I showed you in 10.1.
Sweet.
And tomorrow we will do 10.2. I posted these notes yesterday and the lecture yesterday in my open math. Make sure you go see that so you just kind of know where it is. There's a section, there's a file in there that says notes. It's in there. Again, get out of here if you want to, but I guess I'll show it to you real quick just in case, even though it's kind of a duh.
Could you also post the Zoom link on the top of the My Open Math? I'm just lazy and I don't want to open up the syllabus every day.
Correct. Yeah, I agree. That should be in there.
That'd be nice.
Yeah, it would. I actually did that last term and I forgot about it. I will post the link to this class up here. Let's see, what do you see? Yeah, I'll post the Zoom link to this class up here, and then I have class notes in here. And now so there's a test in chapter 10 and chapter 11. So here, this first file is that. So there's yesterday's physical notes that I've been writing, and then yesterday's Zoom lecture, and then I'm gonna go in there and post 4.6 notes and 4.6 lecture.
Or your screen?
Did I not share that? Fail.
No.
Yeah, so I'll go post the Zoom link up here. And class notes is right here. Course information has got convergence tests, which is a note sheet for this class that we'll be talking about a couple of days. It's got the spring syllabus and these class notes. So chapter 10 and 11 is our first test. So I have a folder for all of the notes that'll be chapter 10 and 11. And so there's yesterday's notes, which is again a transcript of everything I wrote for you. So don't write, be just paying attention in class. Write a little bit, you know, when I say go ahead and solve this problem, but everything I write you're going to have access to, so don't waste your time writing that stuff down. And there's the lecture. That usually takes about an hour after class for that to kind of upload and so forth, so it won't be there immediately. But if you miss a class or you just think I want to watch something again, you can always do that. So awesome. Class officially ends at 9:20. I don't know what it is, but every single day it ends at 9:30. I don't know why, but it just does. So feel
I
free
told
to
you
bail
you
at
should
9:20.
adjust your times.
I can't. It's not legal. You're supposed to have.
Yeah, the Math 261 class starts at 9:30 every other day.
Right.
So
Feel free to bail. I don't mean
Okay.
to be. I'll try to stop at 9:20. It just seems to never happen because I got cool stuff to tell you. All right, get out of here. See you tomorrow.
I have
you. Have
a
a good day.
homework question
Please.
real quick.
Go-
So on 10.1, question 9, I think there's a factorial sign, and I know it means factorial, but I'm not really sure what factorial means.
Good question. We'll be talking about factorial more in a couple of days, but factorial means multiplication. So if you say what's 5 factorial, again, it's a weird symbol. It comes up in probability. But it means 5 factorial means 5 times 4 times 3 times 2 times 1. It means itself times all the numbers, whole numbers below it.
Okay.
And it's buried in your calculator behind the math button. If you hit math, and then you have a list across the top. I'll show this to you. You have a list across the top, and the one to the right says PROB for probability. That's where you find it. It's very buried in your calculator because it's not something you need very often.
All right.
Yeah. So
Thank you.
5 math arrow over to probability. Boom, there it is. Exclamation point. I think it's really funny because it's like 5 factorial. It looks like 5, you know, if you're in an English class. But no, 5 times 4 times 3 times 2 times 1.
Hey Doug, I nerded out a little bit yesterday. I figured you'd appreciate this. You were talking about why they named that formula Gabriel's horn.
Yes.
Actually,